Hello everyone and welcome back to chapter 22. In the previous video, which ran a bit longer than I was expecting, but we needed to finish off that first derivation for the line of charge. And as I mentioned, that is going to be the worst of all of the derivations that we're going to have to endure for this semester. But it is important that we step through the mathematics and we see exactly why these equations are coming together the way they do. And then more importantly, can we use the end result of the equation that we are producing, and can we sort of gauge what is going to happen in the system if we start taking those equations to their extremes. In other words, if we start applying zeros or infinities to certain terms within those expressions, do they blow up, or do they converge to a particular value? Which is what happened with the infinite line of charge. We actually got that to converge down to a finite expression, which is useful to us for estimates. We're not actually going to have an infinitely long line of charge in any of our systems, but given the incredibly small charge particles that we're dealing with, having a expression like that as an estimate of what is happening is actually quite useful. And so to start off today's video, we're going to go back to that default starting equation. This was the expression that allows us to find the electric field magnitude produced by a single point charge. And what we did with the infinite line was we segmented that line into individual infinitesimal charges spread out over infinitesimal displacements. Oops. And we said that as long as the charge is uniformly distributed about the surface, then that ratio has to be the same as the total. And we called this ratio lambda. This was the linear charge density of that line. But then we had to adjust our expression over here because each infinitesimal charge was only going to produce an infinitesimal amount of the field. And from there, we had to set up our integration, and it was quite challenging to say the least, because we ended up with, I think, 4 different variables in our expression and only one integral. And so we spent the majority of the time just figuring out how we were going to substitute different variables for one variable that wouldn't blow up in the integration. So now what we're going to do is we're going to take that same line of charge, except now we're going to wrap it around in a circle. We're going to make a ring of charge. And we want to see what electric field this ring will produce. Now I'm going to go ahead and define the point in space where I want to measure the electric field, and that's going to be directly above the center point of the ring. And the reason I want to measure it there is because I can take full advantage of the symmetry in this system. The great thing about taking this line of charge and wrapping it around in a circle and then measuring everything from the center point of that ring is that every point on this circle is going to be the same distance from the point in space where we're trying to measure our electric field. So up here at point P, I want to measure the electric field, and over here I have my individual infinitesimal charge that I'm going to use as basically a test bed to see what I'm getting out of our expression over here. And so that means I need to know how far away each of these charges is going to be from the point in space. Well, that's going to be easy enough. I'll draw a line from point P down to the charge that I'm using, and we'll call that R. And if we go all the way around the ring, we'll see that every infinitesimal charge will have the same distance of little r from the point P. Likewise, each of these individual infinitesimal charges will have the same radial value as measured from the center of the ring. And now we have another right triangle. We had a right triangle show up with the line of charge, and that was actually beneficial to us because it showed us how we would be able to convert from one variable to another. And the one final thing that we had in our right triangle was this angle theta up in the top corner. But here's the really interesting thing. When we look at this picture, Z is the measure from the center point of the ring up to point P. That's a constant. The radius of the ring, big R, that's a constant. And so if Z and big R are constants, then little r has to be a constant. And if all the side legs are constants, then that means that theta has to be a constant. So, well, what variables do I have then? I need something that I can integrate with respect to. Well, so far the only variable that I still have inside this expression is dq. I'm going to have to go around the ring and add up all the individual charges, and that's what our starting expression here is implying. I'm going to have to integrate both sides. I'll go ahead and integrate the left-hand side right now. dE is going to integrate to E. But now I have to integrate the right-hand side. And K is a constant. Little r is a constant. dq, I'm going to have to add up with respect to dq, but if I do that, the only thing that's going to happen if I just go around that ring and I add up all the charge, all I'm going to get is the total charge of the ring, and then my expression is going to revert back to the point charge expression, which is not entirely correct. If I were to travel very, very, very far away from this ring, then that ring would start to look more and more like a point. And so this expression might become more valid to use. I would be able to treat this ring as a point, but only if I was very, very far away. We need to consider what's going to happen if we stay relatively close to this ring. And to do that, I need to be able to describe how this charge has been distributed in the system. And right now there's nothing in this expression that tells us that. There's nothing in this expression that tells us that this charge has been spread out over the surface of a very thin ring. Except we do have something like that. It's right here. In the previous derivation, we used lambda to tell us how the charge was spread out over the line of charge. But now we've just taken that line and we've wrapped it around into a circle. But there's no reason that we can't continue using lambda to describe how the charge has been spread out. We still have infinitesimal amounts of charge per unit length as we go around this circle. But the one difference that I'm going to make here is that I'm not going to use dx as the infinitesimal length. So I'm not going to use dx as the infinitesimal length. Instead, I'm going to use ds. And the reason I want to use s is because s, oops, wrong color, s, back in geometry, was how we would describe the arc length of a given segment of a circle. And arc length was angle times radius. Now let's not confuse ourselves. This is not the same angle theta that we have in our right triangle there. So let me put a different angle there. But this part actually isn't going to be important to us. All we need to do eventually is add up the total length as we go around that circle. And so after we're all done with our integration, s is eventually going to equal 2 pi r. All right. But now that we have this means of describing how our charge is distributed in the system, we can substitute that into our expression. So we're pretty much doing exactly what we did with the line of charge. We're looking for a more appropriate variable that we can integrate everything with respect to. And so now it looks like my integral is set up with respect to s, which is the arc length going around the circle. And to go all the way around the circle, well, I'll start at some 0 value and I'll go all the way around the full circumference, 2 pi r. And looks like that's it. And if I were to integrate this, the values of k, lambda, and little r would all come out to the front, and I would integrate with respect to my limits, and we'd be all done. And we're like, wow, that's really quick. That is so much faster than what we had with the line of charge. And I agree, but there's one thing that we still need to incorporate into this discussion. You'll remember from the line of charge derivation, whenever we had a charge that was sending its electric field up to point P, so we have this electric field component, which is coming from our little test charge over here on the right. It's sending that electric field up, and it intercepts our point P. But at the same time, as that charge is sending its field up, we have an evil twin over on this side, which is also going to send an electric field up to that point where it will intersect. And our evil twins are comparatively symmetric to one another. They're both the same radial distance away from the center of the ring. They're both the same R value. They both have the same Z and theta values, and so when our electric fields get up to point P and they intersect, they're going to intersect and combine their field components in such a way that the horizontal components of field will cancel out, and the only thing that will be left are the vertical components. And so what we need to do in our integration is we need to introduce a little bit of extra math to ensure that the only thing that we get out of this integration is the vertical components of these field lines. So each of these two field lines will be producing some vertical components, and those vertical components are going to utilize the same angle theta that we have in those bottom triangles there. And this means that the vertical components of those fields correspond to the cosine relationship, because these vertical components here, those are the components that are adjacent to our theta value. And so we need to incorporate a cosine theta into our work. Well, theta is a constant, at least in this expression, and there's really no reason why we can't bring that out front as well. The only thing left that we would have to do still is integrate with respect to ds. And if we do that, we're going to get ds is going to integrate to s. We'll have to evaluate from 0 to 2 pi r. And so our electric field will be k lambda cosine over little r squared times the 2 pi r minus 0 that we get from evaluating our limits. And technically that would be the electric field magnitude up at point P, which happens to be a distance of z from the center point. But if you notice, there is nothing in this expression that says anything about z, which is kind of odd. And so now what our author is going to do, we're going to make some more substitutions in this expression. We're going to rewrite it. Not because we just want to make life more difficult on ourselves, but the reason that we're going to rewrite this expression, it actually has to do with a more practical real-world application. If you can imagine for a moment, you're in a laboratory setting and you want to figure out what is the electric field that's being produced by this charged ring. So we have a ring with a bunch of charge on it, and pretty much everything in this diagram is a constant. We've got r, we've got z, we've got little r, we've got theta. And right now the only values that we need to solve the electric field are little r, theta, and big R. So here's the question. In a laboratory setting, of all of these values that we see in front of us. We've got these 4 different values. We have z, we have theta, we have little r, we have big R. Of all those values, which ones are the easiest for us to measure? So if we had to measure these, which one would be the easiest for us to measure? And your answer should be these 2. We can very easily calculate the other 2 values from the first 2. I thought I changed the color. There we go. And of course it won't rewrite. There we go. So theta and r, those can be calculated by using z and big R. And it's going to be far easier for us to use the measurements of z and r in a lab setting, especially if all of a sudden maybe I decide to switch out that ring for a larger ring of a different radius value. Or maybe I decide to take my measurements at a different value of z. It's very easy to measure the values of z and r, and if I can just use those to calculate the required values of theta and little r, then we shouldn't have any problems. So our challenge for right now is to take this equation and rewrite it in terms of z and big R. In other words, no little r's and no thetas. Okay, so let's see what we have to work with. I'm going to draw the right triangle over here just so we can see it. Okay, so first thing we need to get rid of is r. And we need r in terms of our easily measurable quantities. And this just means Pythagorean theorem. Little r is the hypotenuse of our right triangle, and so little r would be z squared big R squared. Theta, well, in our expression we're using cosine theta, so we will need to replace cosine theta with something involving z and big R, except that the definition of cosine is adjacent over hypotenuse. The adjacent leg to theta is z, and the hypotenuse is little r. And we can't have little r, but we know what little r is, so let's use it. We have z over root z squared r squared. So there's cosine theta. With respect to that triangle, that is what cosine theta equals, and we also know what r squared equals. So let's take our expression and we'll start making the appropriate substitutions. We have k, we have lambda. I'm going to go ahead and put r squared in the denominator right now. So r squared, I would square both sides, and so I just have z squared big R squared. And then we have cosine theta, which is z over root z squared big R squared times the 2 pi r. So that's everything that we have for the expression at this point. Another thing that I would like to do before we start cleaning anything up Now that we're done with the integration process, we can come back and we can revisit lambda. Before we integrated everything, we said lambda was the ratio of charge per unit length for all the infinitesimal pieces, but now that we've added everything up, we can say that lambda is equal to the total charge of the ring divided by the total length of the ring. And the total length of the ring is the circumference of the ring. So we can also replace lambda with its full value of q over 2 pi r. And oh, look what happened there. We have a 2 pi r and a 2 pi r that cancels out. And what we have left is kzq. So here big Q is just representing the total charge that is spread out over the surface of our ring. And now we have to clean up the denominator. Now I've written this out sort of purposefully. We have z squared r squared in a parenthesis set, and then we have root z squared r squared. Now, we can take roots and we can rewrite those as fractional powers. And so a square root can be rewritten as a 1/2 power. And if we're going to be writing everything in terms of powers, then the first term, which didn't necessarily have a power attached to it, is understood to have a power of 1. And now we have a product of two like bases. In other words, if you think back to your days in algebra, if you had two like terms that were multiplied together, then you could add the powers together to get a single term. And that's exactly what we're going to do here. The bases of these power terms are the z squared r squared. And so we have to add 1 plus 1/2, which is 1.5, or 3/2. And there's our expression for the ring. We are done. We have the magnitude of the electric field above the center point of the ring. Okay, well, still that wasn't nearly as bad as the derivation for the line, because as we said, we could have stopped right here if we wanted to. All this other busy work was just getting us to a more user-friendly version of that expression. But now what we want to do is take that more user-friendly expression and consider what happens when we start trying to measure the electric field of this ring at certain extreme points. And when I say extreme points, I mean we're gonna try to stick in values of 0 or infinity. And so let's see. I like to call this the what if game. So what if we were to let z equal 0? What would we get for our electric field magnitude? And so we plug in a 0 for z, meaning that we're right here at the center of the ring. And a 0 in the numerator we have 0 in the denominator, and if z squared goes to 0, then we have r squared to the 3/2 power, which would technically be r cubed. And so what this means is that we would have 0 over r cubed, which is going to be 0. So mathematically, we have an electric field magnitude at the center of the ring, which is equal to 0. But what does that mean? Why is that happening? Well, the reason that's happening is because our infinitesimal charge over on the right here is going to send a field line over to the center of the ring. And at the same time, its evil twin is going to send an equal and opposite magnitude of electric field towards the center of that ring. And this is going to happen all the way around the ring. We're still going to have electric fields being produced by that ring, but when they all get to the center of the ring, the symmetry of our system causes all of the math to collapse, and we get an electric field of 0. Okay, so next, let's try taking z to infinity. So let's take our point P, and we'll move it way far away to infinity. And what are we going to get for an electric field line? Well, up above, if you'll remember, we kind of mentioned that. We said, well, you know, what would happen if we got really far away from the ring? We said that the ring would start looking like a point, and so maybe we could just use the point charge expression for the ring. Okay, that's fine. You can try that. But if you go all the way out to infinity, now we can try this with both expressions. This is the point charge expression, and we also have our ring expression. Well, here I don't have a value of z that I can plug in, but if I go out to infinity, then z and r are both basically going to be infinity, and so I'm plugging in infinity for little r. I would get a 0 for this expression. Over here, if I plug in infinity for z, well, I would have some infinity in the numerator. I would have some infinities in the denominator. In your calculus classes, this would technically be considered an undefined statement, but there are some ways of kind of getting around this. In the numerator, we have a z to the first power, and if we're allowing z to go to infinity, and sorry, that should be an r. If we're allowing z to go to infinity, then the value of r doesn't really matter in this summation. And so the whole denominator is basically going to collapse to a z cubed expression, which means what we really have is a z squared relationship. Pretty much the same relationship as what we had over here. And so if we let z go to infinity, this expression is going to approach 0. So why is that happening? The math is telling us that our electric field is going to go to 0, but what does that really mean? What's happening with the electric fields that causes us to have a zero field measure way up here at infinity? Well, the issue is that you've gotten so far away from these charges on the line that you just don't notice them anymore. You know, you could be looking at someone that's holding a flashlight, and as they get further and further and further away from you, that flashlight becomes dimmer and dimmer and dimmer until eventually you're not going to see that flashlight anymore. Even though they're still shining it at you, the light is dispersing as it travels, and that's what's happening here. These electric fields disperse the further away that we get from the source of those charges, and we don't see an electric field anymore. So that's playing the what if game with Z. So what if we tried that with R? What if we let R go to 0? So if R goes to 0, well, this means that we're going to collapse this ring down to a single point in space. We're going to take all the charge that is currently distributed around this ring, and we're going to collapse it down to a single point. That's what we're doing by allowing R to equal 0. Well, let's see what happens to our expression if we do that. We have z squared r squared to the 3/2 power. I'm going to let r go to 0. When that happens, I'm left with z squared to the 3/2 power in the denominator, which is effectively z cubed. And then we can factor out those z's, and oh, look what we have here. We have kq over z squared, which really is no different from saying kq over r squared. So we are producing the point charge expression by doing this. So we have kq over z squared. So in that case, our ring of charge acts like a point of charge. So the last thing we might try is what would happen if we let r go to infinity. So now we're going to take our ring of charge and we're going to extend it outwards in all directions. But if you do that, you know, as this ring gets larger and larger and larger, are you able to see the edge of that ring? And the answer is no. We could still definitely have a bunch of charge. I would need an infinite amount of charge to be spread out over an infinite circumference. So we're kind of running into an undefined scenario there. But even if we had an infinitely large ring, if I wanted to measure the electric field at some point above the center of that infinitely large ring, how far away are the charges from the point that we're trying to measure? And the answer is, well, they're infinitely far away. And if they're infinitely far away, then we can't see them, we can't register them, we can't measure them. And that's going to show up in the math here. If I put infinity in for r, then the value of z doesn't matter. And I now have kzq over, let's see, infinity cubed, which, you know, that doesn't really matter. This whole expression is going to go to 0. Okay, so this is what I was talking about when I said we want to be able to see what happens to our expressions at given extremes. So now that we have produced the equation that tells us what our electric field is going to look like for the ring, it is important to know the limitations of this distribution of charge. In this case, you know, if I went to the center of the ring, then I didn't get any electric field that I could measure. If I go too far away, in either case, I don't get anything to measure. But here's something interesting. The math is telling us that if I go to the center of the ring, there will be 0 electric field. And if I go too far away from the ring, there will be 0 electric field. So between 0 and infinity, I have 0 at both of those extremes. Does that mean that the electric field is going to be 0 everywhere in between 0 and infinity? And the answer should be, well, no. We can plug some values in here and get some actual finite solutions for the electric field. My big question is, if we are in fact going from 0 to 0, let's see if we can graph this. We have an expression here, or a function, which is starting at, oops, that should be on this axis here. We have an expression that starting at z equals 0, we have an electric field magnitude of 0. And then as we go out to infinity, we have to go back to 0 again for our electric field magnitude. And this implies that somewhere between 0 and infinity exists a maximum magnitude of electric field. And what I want to know is, where is the maximum for the electric field? So at what value of z do we achieve that maximum? So I'll let you go ahead and think about that. I'm going to actually end the video here, and when we pick up with part 3 of this chapter, we will actually discuss how we're going to find the location of where our electric field function has its maximum. But until then, do a little bit of brainstorming, think back to your days in calculus, and see if you can remember how that's done, and maybe even try it out for yourself if you want to. But then we'll come back and we'll go through those steps together at the next video. So see you then.